Hello and welcome to our presentation. My name is Sergiy Tkachuk and I'm excited to be here at the NLP Summit to share our work with you. I'm joined today by Piotr, Szymczak, data scientist in our team, who has been instrumental in developing the system. We both work in the field of ML and NLP and have a deep interest in developing innovative solutions into real-world problems. And in this presentation, we will discuss how we can create a scalable system to identify adverse events from consumer reviews in an autonomous way. We will explore the challenges we faced, the techniques we used, and the results we achieved. Reckitt is the company behind some of the world's most recognizable and trusted consumer brands in hygiene, health, and nutrition, including Airwick, Vanish, Durex, Finish, and more. Every day, more than 20 million Reckitt products are bought globally, and we always put our consumers and people first, seeking for new opportunities and strive for excellence in all of we do and build shared success with our partners. At Reckitt, we take consumer safety very seriously, and we're constantly looking for ways to improve our ability to identify and respond to any concerns as early as possible. So without further ado, let's dive in and explore the motivation behind the application and how it was built. We were motivated to develop our system by some alarming statistics from the Centers of Disease Control and Prevention. So according to CDC, just in the United States, each year, there are approximately 1.3 million emergency department visits caused by adverse events. Additionally, around 300,000 patients require hospitalization for further treatment due to these events. And this number highlights the urgent need to improve the ability to identify and respond to these events. And to further complicate the matters, the volume of consumer reviews across e-commerce platforms is growing rapidly, with millions of reviews across hundreds of platforms in various markets increasing each month quickly. And we believe we can make a real difference in improving consumer safety and satisfaction eventually by developing a scalable system to identify adverse events for e-commerce review in an autonomous way. And let's explore how we approach this challenge. So maybe before we dive into the detail of our system, we want to make sure we're all on the same page regarding some very essential definitions. First of all, what is an adverse event? An adverse event is an untoward medical occurrence that happens after exposure to a medicine, but it is not necessarily caused by that medicine. And this could include, things like falls or other accidents that happen while taking medicine. Next, we have adverse drug reaction, and these are unintended harmful events that are specifically attributed to the use of the medicine. And ADRs occur as a case of and during a significant portion of unscheduled hospital admission, for instance. Finally, we have adverse drug events, or ADEs, and this occur when someone is harmed by a medicine. This can include both ADRs and adverse events that are not necessarily caused by a medicine itself. And it's important to note that our system is explicitly designed to identify adverse events, not ADRs or ADEs. By focusing on adverse events, we aim to improve and provide a more targeted and effective solution for consumer safety. And we'll expand on how we adjusted these official definitions to fit our needs and portfolio later in the presentation. One of the main advantages of using machine learning system to identify adverse events is scalability. Unlike manual rule-based approach that our teams used in the past, our ML system is designed to easily handle large volumes of data, making it much more efficient and effective. Another key benefit of our ML system is built-in multi-language support. And by leveraging the power of machine translation, we can analyze reviews written in multiple languages without the need for separate language-specific rule set. And in addition, our ML system is designed to be self-updating and automated. The system can adapt and learn as new data comes in, improving its accuracy and effectiveness over time. Finally, our system is built in with a robust design, incorporating multiple layers of checks and balances to ensure accurate and reliable results. By minimizing the risk of false positives, or other errors, we can help ensure that our system delivers the most value and accurate information possible. These benefits make our system a powerful tool to identify adverse events and improving consumer safety. And now let's take a closer look at how the system works in practice. I'm handing over to Piotr for this part.
Thank you, Sergiy, for the introduction. So the first important question that we have to answer to tell you how and why we have built the system is the question of why have we decided to create and prepare our own system. Because as many of you probably are well aware of, on the market there are already prepared solutions that enable you to identify adverse events from texts. But we believe that our case has some distinctions that make it important for us to build in-house and to focus on those areas that we specifically want to target. So the first distinction would be a distinction between formal and colloquial language. So lots of the available solutions are built with the intent of recognizing adverse events in medical texts. So, for example, patient reports. So these are texts that are prepared by doctors, by experts, and they usually use language that is strictly professional and medical. So if you take a look at the first example here, which comes from ADE Corpus, which is one of the largest open source corpora to built to identify adverse events with automatic systems, we can see that the text mentions severe mucositis, desquamating dermatitis, prolonged myelosuppression, and neurological toxicity. And these kinds of symptoms are not something that an ordinary person without medical education would use to describe their problem. So if you compare this review to an online review written below, we can see that in an online review we have much simple words. I had a reaction, I struggled to breathe, I could not stop coughing. So these are colloquial terms to distinguish symptoms that appear after taking medicines. And we believe that by tackling the appropriate language, which is the language of the online review or social media post, we make our system more suited to operate in those kind of circumstances. Another important distinction that we see is that we, as Reckitt, are not necessarily only a pharmaceutical company. As Sergiy mentioned, we have three main business units: health, hygiene, and nutrition. And so when it comes to the health products, like Nurofen or Strepsils, we do have to monitor specifically for adverse events. But we also have products from the hygiene side of the business, such as Dettol, Airwick, or Finish, that does not fit within a definition of an adverse event, because an adverse event, as Sergiy defined before, is connected to the use of medicine. And we are aware that some of our products, such as Dettol, Lysol, can also cause harm for humans. That's why we want to build a system who can recognize problems occurring within our entire portfolio, to make sure that we're doing the right thing for all of our consumers. So to fit those cases in the definition of adverse events, we outlined two additional definitions. One is a definition of incident, which is a malfunction or deterioration in the characteristics or performance of a device made available on the market, including use error due to ergonomic features, as well as any inadequacy in the information supplied by the manufacturer and any undesirable side effects. And we have undesirable effect, which is an adverse reaction for human health attributable to the normal or reasonably foreseeable use of cosmetic product. So these two definitions help us to expand the definition of adverse event to fit with our entire portfolio. And for the simplicity reasons, when I mention adverse events further in the presentation, I also mean incidents and I also mean undesirable effects, because those are the things that we want to detect. So the second important question in every machine learning project, a question that is at heart of every one of those projects, is the question of data. So to train a highly accurate system, you have to have a good quality training data. So I want to walk you through what kind of data was available to us, what decisions we made according to the, in connection to the data that was available to us. So first, I want to talk about the data that comes from our internal drug safety organization. So in Reckitt, we cooperate with the drug safety and vigilance teams that collect and report adverse events to the competent authorities, to regulatory authorities. So they also collect the reports in written form that are describing those adverse events. So this is a large collection of data that is processed by specialists who are specifically trained to recognize those types of events. And we have more than 100,000 records of the data available. But with this data, again, we find ourselves with a problem of language that is not very similar to the language that people are using online. So these texts are heavily processed to fit the legal frameworks that they fulfill. And if we take a look at the examples, so it was reported that on an unknown date, an adult female aged 35 to 44 began taking condoms. Or in the other case, HCP reported to the health authority website that about a female consumer who suffered from chemical meningitis. So we both have the highly specific medical language, but also we have very non-naturally sounding reported speech in those comments. So even though the data is readily available for us, we don't want to make it the core of our corpus that is used to train the model, because the language domain is not very close. So what can we actually use to build this system? First, we identified some open source data sets that were created for the purpose of named entity recognition in adverse events detection. And these are data sets which are called narrative based, as opposed to medical based, like the ADE data set that I was mentioning earlier. So these data sets, such as CADC or the PSI-TAR, are collected from patients' narratives and contain much more naturally sounding language. Some of those data sets even rely on the data from the internet, from internet forums where people discuss the medicines. So the language is pretty close to what we are expecting in online reviews and in social media posts. Last but not least, the most important part of our data comes from the internal consumer relations and social listening teams. So this is the data directly from the e-commerce and social media platforms. This data is available to us in very large quantities because it's collected by Reckitt for many purposes. And we, for example, have over 1 million comments coming from e-commerce platforms and from direct contacts from our consumers that are already labeled partially for classification purposes, because they are labeled for internal processes of our consumer relations team. The biggest drawback of this data is that the data is labeled only for classification. So we are not able to do named entity recognition and recognize individual examples of adverse events that occur within a larger piece of text. So to kind of unlock the potential of the data, we had to partner with an external vendor that provides labeling capabilities. And with that, we were able to collect the data set that we're able to use for the purpose of this project. So after discussing the data, we have to discuss the models. So I want to talk about what approaches that we take to modeling and what libraries and what models have we used. So the basis of our approach is formed around transformers, which provide state-of-the-art results in the NLP. We use the TensorFlow as our deep learning API, and we take our pre-trained models from Hugging Face, where they're easy to locate, load, and you can test different architectures and different approaches very easily. So the modeling pipeline that we use is kind of two-step, with an additional step for translations. So as Sergiy mentioned, we leverage machine translation to allow for monitoring of domains from outside of English-speaking world, for example, from China or from many other countries, because Reckitt is also selling its products in different markets. So we want to be able to provide the same level of safety to all of our consumers around the world. So we also include the machine translated data in the modeling data set because sometimes, even though the machine translation has greatly improved during the last few years, we still see that the artifacts from translation are still visible. We want our system to be able to recognize those artifacts also, and to adjust the language that is used by the that is generated by machine translation. We then train a classifying model, which tells us whether a text contains adverse events or not. Then we train an entity recognition module to recognize individual occurrences in 3 categories. So we have indications, we have drugs. So indications are reasons for why somebody took the drug. And we also identify the adverse events, as this is the core of the project. I previously mentioned that we have a lot of data available collected from online sources about our products that we cannot use because they're not properly labeled for named entity recognition. This, however, means that we can use this data in another way. So to not lose the information about what people else are saying about our products online and how they are saying it, we decided to pre-train models that we used for classification and for named entity recognition, using the classical approach taken in training large language models and transformers, which is the mask language modeling, where you mask a portion of the words in a sentence and ask the model to predict those words. So with that, you don't need labels. So we wanted to give the AI the best possibility that we can to actually understand the specificity of our product portfolio and of the way how people are talking online about their experiences with the products. So now I want to take you through the actual models. So the both classification and named entity recognition models are based on the similar architecture. And it's a classic architecture of a transformer-based model for a downstream task. So we take a piece of text, we tokenize it, we input those tokens and attention masks into the transformer, where it goes through the embedding layer and then through multiple encoder blocks. So this gives us a possibility to tune several parameters around the model. First, and probably one of the most important ones, is the type of the transformer you use. So we're experimenting both with classical BERT models, with distilled version of BERT and Roberta, to see if we can improve the speed of the performance of the model without losing the accuracy. We're also experimenting with some newer architectures, such as Google's Electra. Then the second important parameter is the number of trainable transformer layers. So the amount of the encoder blocks that is able to be fine-tuned during the training on the downstream task. So usually we use the pre-trained model that I mentioned in the previous during the previous slide. So we don't want to keep all of the layers in the transformer trainable for the downstream task, because we already infused the model with lots of information about the domain it's operating in. So, but we might want to see whether unfreezing and training one or two blocks of encoder gives better results. Another important parameter is the number of dense layers that is processing the transformer output. So I will be showing you the downstream architectures in a moment. But basically, this is the amount of the fully connected neural network layers that are connected, that are processing the data before the final classification. Then, of course, we have standard parameters like dropout value between the dense layers, learning rate, and the optimizer function. So for the classification model, we want to use from the output of the transformer the CLS token of the last hidden state of the transformer. This is the token that is usually used to perform classification on downstream tasks. And this token is set to have a best representation of the meaning of the entire sentence. So we take the value of the CLS token and we pass it through dense layers with dropout and into a final classifying layer, which outputs a binary flag whether the comment contains another event or not. With named entity recognition, the situation is a little bit different because we want to be able to output a prediction for every single token in a model. So instead of taking just the CLS token value, we take the entire last hidden state and we process it with dense layers into a classifying layer. That enables us to output a single prediction for a single token. So we're able to identify whether the token contains an adverse event, whether it's an indication or a drug. Last but not least, we want to walk you through how we are going to be productionizing the model and what is our plan to adopt the model within the organization to build the trust that our artificial intelligence does its job as it should be doing it. So high-level overview of planned architecture. We will be connecting to all of the major sources of online data that exist within Reckitt. This data will be loaded into a cloud machine learning pipeline, where the data will be first prepared and translated where the need is. Then it will be passed through the classifying model to tell whether these comments are adverse events or not. And the adverse events will then go into the named entity recognition module. And this all will be working. The results of the classification will be stored in SQL database that is going to be used to communicate with the front end modules of the system. So one of those modules is going to be a human in the loop application, which I will allow Sergiy to talk to you about in a minute. And the other one will be a signal system that will be able to notify the drug safety teams when a certain amount of similar events has been detected online in a certain amount of time, to allow us to quickly and decisively deal with the problems before they become known to us through other channels. So this system also will collaborate with other systems that are monitoring the reports that the Drug Safety Office is compiling to the regulatory authorities. This will give us a better overview of how our products are interacting with the real world to ensure that the safety is met. So for the last part, I will be passing voice to Sergiy, and he will tell you about the way that we're driving the adoption of the tool.
Right. Thank you for passing over, Piotr. So as many of you recall, one of the biggest challenges in developing a supervised machine learning system and any other system in general is the need for label data. And in order for our system to learn and improve, it needs to be trained on large data set of consumer reviews labeled as either containing or not containing adverse events. And obviously, we will want to have more granular classification later on. It will require even more labeling efforts. And however, labeling data can be a time-consuming and challenging process, especially when it comes to identifying more complex and subtle adverse events. And to address this challenge, we've implemented a human-in-the-loop process where kind of internal subject matter expert work alongside the ML system to help identify and label reviews that may be more difficult to classify. And this approach has several benefits. So first, it helps ensure that our system consistently produce high quality results, even for more complex or nuanced reviews. Additionally, it allows us to continuously improve the accuracy of our system over time, as the subject matter experts provide feedback and insight that can be incorporated into ML algorithms. So overall, our human-in-the-loop process has been a critical component of the system's success and allowing us to overcome some of the challenges inherent in developing a supervised ML systems to identify adverse events in general. Here is also a simple yet well set up UI that we developed with the help of our internal front-end team, where people can actually react to certain adverse events that were identified by ML algorithm, report them, escalate, or classify to other class that it may fit more, and then system will take this input and relearn and to be better the next time. Thank you everyone for having us. Happy to answer any questions, and feel free to reach out to us via LinkedIn or email later on. Thank you.